Very good. So it's my great pleasure to introduce the final keynote of the first virtual ICSME by Tim Menzies. He's an IEEE fellow. He's a professor for computer science at North Carolina State University in the US. His papers are among the top 20 most cited in software engineering. He's earned more than $12.5 million in research grant, graduated an impressive number of 43 graduate students so far. But to really introduce him in the context of this conference, I need to briefly share my screen. Give me a second here. Make this full screen. And in fact, we need to go back all the way to 2007. Here we see the title of a TSE paper. You will be familiar with TSE. Title of a TSE paper by Tim Menzies and some colleagues called Data Mining Static Code Attributes to Learn Defect Predictors. This paper was very well received, as you can see, more than 1,000 citations. But promptly after, my general co-chair, Hongyu Zhang, he wrote a comment on this paper that included sentences such as, the models built in reference 1, which is the Menzies paper, are not satisfactory for practical use and should be improved. This, of course, was promptly responded to by Menzies and team. Let me just move the audience out of the way here. Who published, I think, pretty shortly after this, published a comment saying, okay, problems with precision, comment on the comments on data mining, static code attributes, and so on, saying that, you know, the Zhangs argue that predictors are useless unless they have high precision and recall. We have a different view for 2 reasons, and so on. So you see, you know, the start of a nice academic fight back in the late 2000s using TSE as a platform. Of course, this is not the end of the story. And in fact, shortly after, in November 2009, in fact, Tim Menzies visited Dr. Zhang in Beijing. And as you can see in the picture, maybe, they had some really nice conversations. And in fact, one of Dr. Menzies' PhD students at the time, then in 2010, Viola Peters, went to spend about 3 months with Dr. Zhang in Beijing at Tsinghua University. And out of this collaboration came a variety of papers, all of them well cited. So what can we learn from this little anecdote? In academia, it's important to keep your friends close and your enemies closer, because your enemies aren't really your enemies. They are actually the best colleagues you have, and in many cases, your greatest inspiration. And it's also important to play nice with the colleagues who might criticize your work, because, you know, one day they might be general co-chair of a conference and invite you to give a keynote. And it's my great pleasure to hand the microphone over to Tim for exactly that keynote. Tim, over to you.
Great. I'll just find the share screen button, and I'm hopefully got it there.
Before Tim start? Yeah. Okay.
Continue, share screen, share. Okay, are my slides on the screen? Can you hear me?
Yes,
yes.
I can hear you. And,
okay,
yes to both.
Great. Well, thank you for that introduction. I really think that's a lesson we need for the. We talk a lot about social media and connectiveness in the year 2020. That includes the academic community. Having a sense of play nice with others and work well with others, very powerful for my own career. I highly recommend it. It's fantastic to be here at ICSME. I was general chair of ICSME with Nicholas Kraft in 2016. And I've always thought ICSME is not as hidebound as certain other conferences. Here, ideas might get a better airing than they may be at certain other venues that might be a little bit more obsessed with their status and position in the world. So ICSME is a very exciting conference. It's fantastic to be virtually here in Australia giving this stuff. There's been some recent talk with ICSE and ASE and FSE coordinating better. And they talk about positioning these conferences around the world, so that the hubs of software engineering around the world, the major centers of SE research, all get a major conference regularly. And what's very exciting to me is that in all those conversations, Australia is now considered to be a major hub of software engineering research. And that wasn't true 25 years ago when I abandoned Australia and ran away. So the current high status, the high central position of Australia in international software engineering research, as recognized by the steering committees of FSE, ICSE, and ASE, didn't exist. And the current high status has nothing to do with me. And the people we need to thank for making Australia central to the international SE community, some of them are on this call. Like Hongyu Zhang left Tsinghua University to set up shop in Australia. Think about what that means. An international researcher of Hongyu's reputation leaving Tsinghua University, China's premier institution, and saying, I'm going to come to Australia. Christoph deciding he's going to relocate in Australia. That sends a message around the world that this place has made it. Now, there's too many people to list who put Australia on the map and made it central. And if I start listing them, I'll miss out people and people will be annoyed. I feel I should put John Grundy on that list and make sure that everyone knows that John Grundy for decades has been working to make Australia central in international software engineering. I feel it would be rude of me not to mention my beloved colleague, Barak Turan, and then we start with all the Monash people, Shir, Kla, and after that just cascades, and there's too many other people to congratulate. But I just want to take a moment to congratulate Australia becoming a central hub of software engineering research around the world. ASC 2020, ICSME 2020. And I think it's known that ASC 2021 is going to be in Melbourne because of all the virtualization problems with ASC 2020, which problems they addressed and did very successfully. We still want to have a conference. So Australia is now a central hub of software engineering research in Australia. So congratulations to Australia for that. And I can take absolutely zero credit for that distinguished place. What I want to talk about is the future of SE and how it's very AI related. I want to introduce you to two ideas, one called Software 4.0 and another one called GATE, which is my way of implementing Software 4.0. I want to talk about we need a different kind of software engineering for AI because software engineering, AI for software engineering is different. And one of the things that makes it different are some astonishing properties of software engineering data. Astonishing in their simplicity. Such simplicity is highly desirable, and I'll end some talk about not just deep learning, but deeper learning. And this working. Now, while I've got you here, let me just say that we're having a call for papers at the IEEE Computer Conference Journal. This call for paper is 30th of July, 2021, so you've got time to work on this. The call for papers, its URL is tiny.cc/AISE21. That's tiny.cc/AISE21. And that's being edited by Atif, myself, and Alexander. And we look forward to reading your exciting papers at a special issue on IEEE Computer on AI and software engineering. Are we ready? While I'm here, let me point out that bottom left of this slide is the URL for this slide, tiny.cc/TIM20. That's tiny.cc/TIM20. So there are some URLs to look at. So let's talk about why I think the future of SE has a lot of AI in it. Well, firstly, I want to say that AI needs a lot more software engineering. Let me just pause there for a second. Is my sound okay? And are the slides advancing okay? Getting a thumbs up? Very good. So I think that AI people need to know a lot more about software engineering. And I think software engineering people need to know a lot more about AI. If you look at the standard picture of any deployed AI system, like the one Scully offered us in his technical debt paper at Google, the tiny black box in the middle of the bottom diagram is what you might call hardcore AI at Google. And surrounding it is all the other software engineering materials. Now, this picture has changed since 2015. Now we have different boxes, but the general picture is the same. There's a hardcore AI in the middle surrounded by a lot of software. And all that software needs installation and configuration. It needs maintenance and interfacing. It needs testing. It needs certification, user support. It needs usability additions. It needs packaging. AI software is software. So AI people need to know a lot more about software engineering. If you want to know more about that, I've got a paper on this, the 5 laws of SE for AI at IEEE Software. Now, not only do AI people need to know more about software engineering, but I think the SE people need to know a lot more about AI. Now, when I tell SE people they need to know a lot more about AI, some people push back and say, excuse me, there are other conferences that do AI. We'll just do software engineering and we'll let the AI people do them. And I'm saying, well, you know, if you think AI is not a software engineering problem, there's a long history of people saying that X is not a software engineering problem. And then a decade later, we realize X really is a software problem. For example, did you know once upon a time that users weren't a software engineering problem? Dijkstra's famous quote from 1979 that users cannot be precisely defined and therefore have no place in software engineering. So once upon a time, users weren't in software engineering, and testing wasn't once in software engineering. If you look at Highland Mills Clean Rooms proposal, 1985, we take the compiler away from the programmers, and the programmers have to write provably correct code, which gets thrown over the wall to a separate testing team. Now, just pause there for a second. I'm going to take away your compiler. I'm going to take away your Python interpreter. I'm going to take away your IPython notebooks. And you're going to have to just write code in a text processor. Think about that as how you want to do software engineering. I think not. Once upon a time, requirements wasn't part of software engineering. Requirements was the thing that happened before software engineering started. Once upon a time, we didn't do deployment. There was no idea that we could get so much feedback from the same people doing DevOps. And once upon a time, AI wasn't about software engineering, but just consider all the keynotes at ICSME, just consider all the machine learning related papers at ICSE, FSE, and ASE. Software engineering really needs to know a lot more about AI. And one of the reasons that that's true is that I believe the future of us is we're going to become midwives. And I mean that in the complete sense of the midwife metaphor. We're going to be the people helping other people give birth to their ideas. Because I think that software is like astronomy. And astronomers don't just build telescopes. Yes, astronomers have to learn how to grind a lens or whatever the X-ray equivalent of that is. But after you grind the lens, you look through the telescope to see something. Now, software engineers have to build tools. We have to do bracket matching. But after we build the tools, we actually use them to do something. And in the modern world, we use that to do everything. As we move into the world of not just the Internet of Things, but the Internet of Things that matter, we find that software runs the world. It controls what we can control. It controls what we see in the world. It controls how we touch, how we do, how we even talk to each other in the world. And so software is literally everything. And software engineering must now be about everything. We're going to be the people doing midwives, helping other people curate things. And so, sorry about that. And so let's talk about engineering principles for this sort of curation of knowledge. And for there, I want to go to something that I call software 4.0, and I want to talk about something called GATE, software 4.0 and GATE. Now, software 2.0 is people automating things. And I think if we take that and if we multiply that by a collection of AI algorithms that understand people and people that understand AI algorithms, we get something much more than software 2.0. In fact, I've even put it up as an exponent. And so software 2.0 times AI algorithms that understand people plus people that understand AI algorithms takes us to software 4.0. And as you know, software 1.0 is traditional manual development. And in software 2.0, there's usually two teams. One team is manually sorting out what examples to give to some optimizer to do some task. And the other team does all the surrounding tools. Now, what I want to say is I've done an awful lot of team one stuff. And the more I do team one stuff, the more I know there are more AI tools that I can lend to team one to make their life better. And so if you look at what happens inside the team one work, organizing the optimizer, I think if you lean in there and double click on that activity, you can find really good ways for people and AI who understand each other to work together and do better. And so what I want to talk about is not just AI for the team one software 2.0 people, but everybody. I want AI for all, AI understanding people and people understanding AI. And one reason I'm saying that is I want us all to know absolutely at the core of our soul that humans are part of the AI development cycle. Humans are part of the AI development cycle. If you look at any description of AI deployment, if you go to the Microsoft paper at ICSE, SEIP 2019, you'll see this diagram. And you've got your model requirements and data collection and data cleaning and feature engineering and model evaluation and model monitoring. Now, the Microsoft people do mention some feedback loops, but my feeling is they're not mentioning the human role in those feedback loops. Now, we've done an awful lot of work with those feedback loops. And what we find is that there is tremendous feedback of humans and human role in these feedback loops. And so if you look at all the different ways people are involved in these feedback loops, it's not just like the AI algorithms work, but at many, many points, we come back with insights that we want humans to check. Is this the right way to label stuff? Is this the right way to divide the data? And in particular, can you see the very long arrow starting at model evaluation and going right the way back to requirements? Anyone who's done model-based multi-objective optimization knows that you can start with the goal of doing A, B, C, D, E, and then when everything comes out, you realize you can do A, a little bit of B, some of E, and that's product one. And in product two, you can do B and C and a little bit of A. So what you have to do is go back to the business users and say, hello, we're your scientists researching your domain. You've given us everything you've told us about the domain. And when we come back to you, we think the world divides into 2 or 3, 5 things. The thing you told us to do actually has a whole bunch of choices. Let's talk about that. And so I'm saying humans are an essential part of the AI process. And I want to support that. And I want to talk about the engineering requirements of AI and humans talking together. And one thing we know about people is that they're very busy. You don't want to spend too much. They don't want to spend too much time on any one thing. I don't want to see the blue curve on this graph. I don't want to see people walking around and finding things in some linear manner. I want the red curve. And in the red curve, the humans and the AI are talking to each other. And the human and the AI is trying to work out what the human wants to do. And once the AI starts working it out, it rushes ahead and starts bringing back better examples. And the human says, no, you got it all wrong. I don't like that at all. And the AI says, sorry. I'll adjust my models. And then it starts bringing back what you want. And the human says, yep, I know what's going on. Thank you. Just complete the task for me. And you get the red curve. And of course, this is sort of the standard active learning loop. There's a bunch of examples that we haven't labeled yet. And what the active learner does, it comes along and it labels those examples. And then after a while, you get the curve, which we can see bottom right. And in that curve, if I find the thing that does it, okay, I can't find the, God bless you. Okay, so in the bottom curve, there's an x-axis along which people make decisions about what they like. And we'll call those events. You can see events 1, 2, 3, 4, 5. And as the human decides things, the optimizer kicks in and you see an S-shaped curve of things getting better. Now we've applied this loop in any number of applications. Active learning for finding relevant papers. We go to Google Scholar, we say defect prediction and get 10,000 papers. And using these tools, we can find the 50 papers that you think are most important. We've used these tools for reading a code to find security violations. We've used these tools for reading GitHub commits to find self-admitted technical debt. We've used these tools to help labeling examples in active learning. And in all these cases, the human and the AI kind of hold hands and set off together to explore the world together. And if you want to know some engineering details under the hood, shown at left, this is the standard Parzen tree structured estimator story. And I'm saying it's more general than just TPE. So what you're seeing on the left at the top is that, we've looked around the world a bit and we've found 5 really awesome examples, which we'll call alpha. And we've found 5 really bad examples that we call beta. And at the bottom left, we've built a model describing beta and a model describing alpha. And here you think the models are just Gaussian. If it was multidimensional, we'll do naive Bayes or random projection or any other methods, to build a model describing beta-ness and a model describing alpha-ness. Now, the way we use this model is we use it to solve a problem. And the problem is that if we do any sort of generate and test process, test is usually orders of magnitude harder than generate. If for most problems, you can you can generate billions of possible solutions in about a minute. You run your theorem prover, you do just, you run a fuzzer. Like anyone who does fuzzing and testing is doing generate and test. Now, the thing is, we can generate billions of options in a minute, but testing them is much, much longer. Supposing every option has to be checked by a human. Anytime a human is involved, things get slow. Supposing you need 2 humans to check that one human's not making a mistake, it's now twice as slow. Supposing you're doing hardware, software, co-design, and every one of your ideas has to be built as a car and then tested. Supposing every one of your ideas means you have to recompile the entire software code in the test suite, it's slow. So you want to generate a lot of things, but try the least number of things. So in between generate and test, we put an assess stage, and that assess stage uses the alphas and betas that you've just seen on the screen. Now there's a lag on the screen. Okay, so let's say you've got the models for alphas and betas on the screen. Let's say you want to do active learning like on the previous slide. If you've got something that tells you if you're alphaness or betaness, if you can find some point where your alphaness equals your betaness, you're in the point, the uncertain point between 2 ideas. And that's a really great place to sample. I got to say that Zhe Yu, who does this stuff, is now at Rochester. He now tells me that after a while, you jump away from alpha equals beta to another region, and his papers are great to read about that. But optimization is just find me things that are very alpha-ness and very low on beta-ness. So maximize alpha, minimize beta, and taboo search, like you're testing, trying to find things you haven't seen before. Try to pick things that minimize alpha plus beta, and planning is take your current situation and add in things that are really common in alpha and take away things that are really common in beta. And now you've got one more idea to try, just one more next idea. And that means you try, do the slow thing, and that generates one more point on the charts on the left, which means we do after G, which is guess, and after A, which is assess, and after T, we try. E is expand. We expand the model on the left, so the next time we go around, we have a better way of doing assessing. Now, if you ask me, what am I talking about here? Am I talking about classification? Am I talking about optimization? Am I talking about configuration? Am I talking about classification or active learning or planning or sensitivity analysis? I say yes, I'm doing all those. And if you ask me, am I doing cross-entropy learning or taboo search or Parzen-Rosenblatt windows or Bayesian parameter optimization, I'll say yes, I'm doing all of those. What I've just shown you is the great secret. What I've just shown you is the engineering framework that we've been using in my lab for decades. Dozens of graduate projects finished, hundreds of papers, all based around this one slide, generating tar3, star, XMO, Bohr, lace, witch, Gale, Dodge, Flash, Emblem, Snap, and we're not finished yet. So this is my engineering framework for software 4.0. It might not be the best one, we can certainly talk about it, but I hope I've given you some sense of what I mean by software 4.0 and GATE, guess, assess, try, expand. Now, the reason I'm so interested in these algorithms, the reason I want, as a engineer, I want to be able to reach in and refactor different AI algorithms from different sources and mix them up, is that I know when I do my AI for software engineering, I can't use the AI tools off the shelf. They need customization. And who are the people that can customize software? Who are the best people in the world to ask to customize software? Well, it's software engineers, it's you and me. So I'm going to say that if you really know about AI and software engineering, you'll be changing your AI tools a lot. Let me just explain why you need to do that. I'm saying AI for software engineering is different. I should say we should stop using the AI tools off the shelf without adapting to software engineering. And I'm not the only one who says that. People who do information retrieval for software engineering tell you that there's certain dumb assumptions that come from non-SE about word frequency, for example, and word importance. And the people who do IR for SE fix those assumptions and get better results. The people that do sentiment analysis, they say, excuse me, you're doing sentiment analysis on GitHub comments and you're using a model trained on the Wall Street Journal or a model trained on Wikipedia. Don't do that. Train your model on SE data. And there are people that look at the parameters we get on the learners we get from the AI community, and they say, you know, those parameters aren't good for SE systems. Before you use a learner on SE data, you want to do what's called hyperparameter optimization. So if you're doing case nearest neighbors, you have to work out what the right K is. And there are so many results showing us that how much better you can do if you take an off-the-shelf AI tool and modify its parameters. For me, the best example I have for how screamingly different AI can be, it's when I said, look, I want to implement a software engineering goal using an AI tool. Schlomenbrion 2006, Weicker, Bell, and Ostrand 2004. They'll tell, and a repeated result by many people, most bugs live in a small part of the code. So don't look everywhere. The ideal defect predictor finds most bugs in the smallest part of the code, because after the defect predictor terminates, some secondary process wakes up and looks at the code. And if that secondary process is a human reading the code that you think is defective, you want to minimize the x-axis on this graph, how much lines of code to read, while maximizing how many bugs you find recall. Now, the AI tools we get off the shelf are typically developed for accuracy, which is nothing to do with maximizing recall and minimizing lines of code. And on the screen right now is a red line. And that's when if I use something called C4.5 or J48 if you're a Wecker person to do this problem. And you can see it doesn't get very good. It only gets about 30% recall. I can get to 80% recall using something designed using that GAT thing I showed you just before. And I can do much better by customizing tools to SE. So SE needs special kinds of learners. Stop using off-the-shelf AI tools without adaptation. Now, one place where that adaptation can be particularly powerful is in response to special features of SE data. Now, what I want to tell you is some SE data is astonishingly simple, and we can exploit it to do great things. Now, the key word here is the sum. I put sum around in brackets. If someone tells you that sometimes things are really simple, they're sort of duty bound to do two things. Firstly, show you how in the simple zone to do crazy great new things. And secondly, to come up with a warning light that says, stop doing simple things, your world's actually complicated. So pretty soon we're going to get to the point where we're going to have an x-axis of complexity, and we're going to see data sets where very simple methods work and do great things, and data sets where very simple things don't work. So if someone says, I'm going to base my thing on a simplicity assumption, you really need to say, excuse me, I'm not going to buy what you're saying unless you can tell me when simplicity doesn't hold. Okay, then, so Prem Devenbu, Abram Hindle, various people have talked about software naturalness. And what they tell us is that even though code is potentially arbitrarily complex, the code people actually write is repetitive, and it can be simple statistical models can tell you a lot about it. And this can be levered for many software engineering tasks. So for example, if you look at any natural language, and here we're looking at Esperanto, Latin, Ukrainian, English, Slovakian, Romanian, what we find in natural languages, there's a small number of things we do a lot, and there's a large number of things we do very rarely. So if we take all the words in English, for example, and sort them by their frequency, if the ith plus one word occurs at half the frequency of the ith word, you get a graph like this. Now the y-axis here is logarithmic. If it was linear, you'd see a massive great spike on the left, which decays very quickly, and then a huge great plateau. So a massive spike of a small number of things we do a lot, followed by a plateau of a large number of things we do very rarely. Now this occurs in natural language. It also, and as our distinguished co-general chair Hong Yu Zhang told us at WCRI 2008, it also occurs in Java code. So Java, in fact, the Zipf's constant is lower. Not only is natural language simple with its repeated structures, but our languages that we write are even simpler than the languages that we speak. So there are repeated structures. Okay. Now, how do I measure that? I mean, I've made a theoretical case that there's simplicity in SE data. Let's measure that in a precise mathematical way. Let's take two populations of data. Now in red, I've got 37 problems from the UCI database. And the UCI machine learning repository is a space that a lot of the algorithms that we use were certified using UCI data. And I went to a standard set of machine learning papers and found, diabetes, labor, iris, the usual suspects. And then I went to my kind of software engineering, defect prediction, issue tracking, predicting GitHub issue close time, predicting bad smells. The issue tracking one, number 6, that's a very complicated text mining problem. And I asked, are the software engineering problems simpler than the non-software engineering problems? Now, to measure that, I used an idea that comes from astronomy, actually, called intrinsic dimensionality. And so intrinsic dimensionality, we're probing a data set to work out what is its underlying dimensionality. Now, let's explain that. We've got Tim and we've got Tom. And Tim lives out in the suburbs in flatland, in the houses that just go in the XY dimension. And Tom lives in downtown in some very crowded apartment blocks with people all around him. Now, Tim, living out in flatland, if he walks in the X and the Y and the Z dimension, he's going to find friends if he walks in X and Y, but he's not going to find anybody if he walks in the Z dimension, because in this example, there's no basement and there's no cellar. Now, Tom, living downtown, if he walks in the X and Y dimension, he's going to find people, unless he walks too far and walks off the balcony. We'll ignore that edge condition. But if Tom walks in the Z condition, he'll also find people. So we have an equation. We have a measure of how much more data we find. So if there's a lag here right now, I hope this comes up soon. So what we do is we start anywhere, we walk away from where we are, and we ask how many more people do we find. So the plot that just showed up, the x-axis shows how far we're going, and the y-axis shows how many more people that we find. And the slope of that graph is a measure of intrinsic dimensionality. Coughing, hang on. Beg pardon. Now, bottom right, I've applied that to the SE and the non-SE data. And what we see is the SE data is 1/3 as complex as the non-SE data. The SE data has a mean intrinsic dimensionality of 2, the non-SE data of 6. Now, what's important here is that the non-SE data, the red ones, is where a lot of our data mining tools came from. So we in software engineering are using tools that were built for things that didn't assume repeated structure, that were much more complicated. So can we do better? Can we exploit that simplicity? Well, all right, how about better testing? Like if you look at what Galzar and Zane did with Big Test and Big Fuzz, they're trying to do scripts testing very large big data applications. And what they said, what we can't do is test all possible combinations of the data on our cloud server because that's just too large. Instead, let's just look at our application logic and trace out the actually used paths and write down the constraints that exist down those paths. And what they found was, for all their big data scripting applications, they found that for income aggregation and movie ratings and airport layover and commute type and grade analysis, etc., they only had 6, 5, 15, 11, 4, 30, and 6 unique paths inside their system, which meant testing their system only had to exercise those paths. And that turned out to be, that reduced their test sets, and these are real numbers, 10 to the 5, 10 to the 8. This is how much they could reduce their test suite tests. And their tests ran 200 times faster by reflecting on the structure of their systems. They matched the complexity of their analysis to the complexity of the data, which I think is just fantastic. Another thing we can do if we recognize the astonishing simplicity of software engineering data is we can write AI that is auditable. Let's talk about the complexity of you auditing my ideas. And in my software 4.0 loops, the complexity I submit can be measured by 2 numbers, alpha and beta. And alpha is the number of human events, the number of decisions people made about, yes, this is relevant. So in the little tiny chart on the screen right now, there are 5, alpha's 5. The human said 5 times, this is relevant, this is relevant. Now, beta is the size of the model. And if you're talking like support vector machines, the size of the model is the number of vectors closest to the hyperplane. So you can see there's a hyperplane dividing the data on the right-hand side, and there are lots of blue dots and lots of red dots, and most of them don't matter. The only ones that matter are the nearest blue and the nearest red dots to the green boundary. Now, if we go to the literature reviews where we're reading 10,000 papers, or if we go to security where we're trying to find security violations and we're reading 28,750 methods. Or if we're looking at technical debt, self-admitted technical debt, and we're reading 6,000 commits, here are the alpha and beta numbers found in this rig. Alpha's like 100, 271, 300. So only a couple of hundred times did someone say, yes, this is an example of what I want. And that's all we needed before the AI could take over and say, I now know what the human wants me to do. I'll go away and do it. And if you look at the size of the model generated this way, it's only 100 vectors or so or less. Now, it might take me a week to review alpha and beta for these domains, but it is possible. I can talk about auditable AI. AI where someone can lean in and say, I don't like decision 3. I'm going to reverse decision 3. Then you could run all the events after decision 3 and see what happens. So I'm talking about auditable AI because I know how to simplify the internal structures of these things. And then here's another example of simplicity, it's privacy. So Fiola Peters was very interested in what I was saying and said, well, if you're right, if there are repeated structures, then only a small number of data points are enough to sample those structures. And that means there's only a small number of dimensions that characterize the data. So she went to defect data that tried to predict for defects per lines of code. And each one of these lines is static code measures of the class. And she said, okay, so I can ask how well each column predicts for the target class separately. You can use info gain, and Fiola had her own measures. I can also ask, how important is each row? So she clustered the data and find samples from each cluster. And then she sorted the columns by how well they predicted for the target. And then she sorted the rows by how well they were represented the centrality of the data. And then she said, throw away everything else. So down the bottom here, we've kept only the things, the columns that most predict for the target, and only the rows that are most simple. And then we don't share the rest of the data. So the data we don't share, 100% privacy. And for the remaining data down there, we do some mutation and we get 80, 90% privacy. And so the total effect is privacy really, really high. And what we found was for effort estimation and defect prediction, a simple k equals 2 nearest neighbor in that tiny little corner of the data did as well as using the whole data. And this is a wonderful example of how we can exploit the privacy, the simplicity of SE data in fantastic and novel ways. Another thing we can do is better hyperparameter optimization. I said before that the default settings we get from our AI tools are really bad. Like you can improve them dramatically with some automatic tuning. Now, left-hand side of the figure on here, you can see an x-axis. And the most left-hand point of that is called C5.0. And there's a little blue dot above that. And then above the blue dot is a red triangle, way high, way up on the top left of that figure. And the difference between the blue dot and the red triangle is how much C5 improved before and after we applied some automatic tuning methods to specialize that learner to that particular data set. And you can see that before tuning, compared to a bunch of other neural net methods and other methods like random forest, this decision tree learner called C5 doesn't do very well. And after tuning, it's doing best of anything else at all. So that says we should do tuning. The problem with tuning is there's such a very large space to tune. So I went to the literature and I found all the papers that talk about tuning and parameters. And I listed all the options people talk about in the literature. And what I found was I was looking at about 10 to the 9 options. So what I realized, if I wanted to turn all my blue dots into red triangles much higher, I had 10 to the 9 things to explore. And that just sounds like it's just not practical, just not going to work. However, if these hyperparameters guide the learners in different paths along the data, and if the data comes from software projects that have repeated structures, it's reasonable to assume that many of these parameters in the middle column are superfluous, that many of them will mean the learner will end up on the same paths inside the data because there's only a few paths inside the data. Let's check that. On the right-hand side, I've taken the false alarm and recall. It's the output. If I configure a learner using the stuff in the middle, that's the input to the learner, and the output is a recall and false alarm number. Now I'm going to take a dart, a very fat dart, and throw it at random at this output space. And by that means I'm going to say, I'm going to pick anything at random from the middle stuff, and that's my dart. I'm going to throw it at the output space. Now can you imagine the dart stuck on one of these cells? Now I'm going to build another random dart, pick at random from that middle space, throw it at the output space. And if the second dart lands near the first dart, I'm going to say, hello, inputs, you've got two things that are doing very similar. Rejiggle the weight so that I avoid things that end up generating similar conclusions. And so this is an algorithm called Dodge, and it's a taboo search across the output space. And what we do with Dodge is about 30 times, we pick at random from this space of 10 to the 9 options. 30 times we pick from 10 to the 9 options, and we just try to avoid things that end up going to the same place. This won't work. If the data is fundamentally complicated, this will not work. If the data is fundamentally very simple, we should do pretty well with this dumb as all hell Dodge taboo search. Let's try it. Let's go back to our data sets we looked at before and recall these fell into two groups. The red zone were the non-software engineering data sets from UCI. The blue are the things we're seeing from the software engineering analytics literature. And when we'll take all the data and sort them by their intrinsic dimensionality along the x-axis. You can see I've highlighted the region where the SE data comes from. Like the SE data has a mean intrinsic dimensionality of 3, and the non-SE data has a mean intrinsic dimensionality of 6. And you can see that in the zone where we find most of the software engineering data, 80% of the time or more, Dodge does better than anything else. Now, by anything else, we went to these data sets and said, what's the prior state of the art in this field? We implemented that. We ran the prior state of the art, we ran Dodge. And what we found is Dodge is running about 30 times, evaluates 30 things. And prior state of the art would do things like genetic algorithms, 10,000, 100,000 evaluations. And the only explanation I have for why 30 random trials through a hyperparameter optimizer works as well as a genetic algorithm doing 10,000, 100,000 trials is the SE data is fundamentally very simple. Okay, now, so not only is SE data very simple, and I now demand that you spend some time thinking how you can exploit that data, such simplicity is highly desirable. I don't think it's good enough that AI engineers are saying we don't understand our software. It was terrible for me to watch the Social Dilemma and see multiple engineers documented on video saying, we don't understand our AI software, and very few people do. That's just not acceptable. If you want AI that is accountable, transparent, inclusive, and can integrate with human agency and allows human insight, may I recommend Software 4.0 and the GATE model that I gave you. If you think about that loop I'm talking about, this is auditable. People can audit this thing. They can lean in and say, I don't agree with conclusion 3, let's change it, and let's run everything after that and see what happens. I want to look at the model that you've built. I'm saying that I'm designing systems that can be audited and understood by people. And if you look at what Microsoft, IEEE, the European Union are saying about what it means to write ethical software, this is words you should be knowing. What does it mean to write ethical software in this modern era? They're saying words like accountancy, accountability, transparency, human agency, oversight. I know how to do that with Software 4.0 in GATE. If you don't know how to do it with your AI systems, then there's either something wrong with your AI systems, or there's something wrong with how you've been trained to think about AI. I recommend people stop thinking. I recommend that training for AI doesn't start with here's decision trees and here's clustering, because then people think about these algorithms as different things. I think we should stop thinking about these algorithms as different things. If you think GATE and map everything you know as sub-operators into GATE, that encourages a refactoring engineering mindset where you as software engineers can combine insights from different approaches in one thing. Okay, so at some point someone's going to ask me about deep learning, so let's just get to that right now. And in preparation for this talk, we went through and we said, let's look at the deep learning papers in software engineering. And we went to the last 10 years, we looked at the senior venues and we said, what are the papers that have received at least 10 citations per year? And what we found is this sample. And we looked at RNN, which the student decided to call CS for some reason on this curve. So RNN, convolutional networks embedding, feed forward, miscellaneous, some weirdo things, or variants, we'll just call them DNN2, different deep learning algorithms applied to code synthesis, code comprehension, language modeling, everything. Now, the first thing I want to say is deep learning has been applied successfully to a narrow corner of software engineering. It has not swept the field and replaced all other methods. The second thing I want to say is that sadly, nearly half the time, people don't compare their deep learning to non-deep learning alternatives. And I think that's a methodological error. Sometimes people do hyperparameter optimization, but not what I'd call hyperparameter optimization. They might twiddle a few numbers or do some stuff. I'm happy to say that round about a quarter of those DL papers do what I would call decent hyperparameter optimization. That's great news, but I'd rather it wasn't 22 out of 94. I'd rather it was 94 people tuning these things. As to how good deep learning is, let's go back to those data sets we looked at before. GitHub issue close time, defect prediction, text analysis of issue reports, etc., etc. And let's compare DL to the best thing we can find that's not DL. So in this curve, if red is above blue, DL is doing better than the best non-DL option we can find. And you can see that on the right-hand side of the graph, there's lots of examples where DL is doing better than the best non-DL alternative we can find. Now, the green is the statistics. The green is the statistics. If you're high up on the green, DL is significantly better than non-DL. These are runs done 20 times, distributions, looking at things like that. And so we will acknowledge DL is better than non-DL when you're high up on that green. And we see firstly, DL doesn't sweep the field. It's usually better than non-DL, but only for recall. If we go to other measures like false alarm, we find that DL does not win very often, and there's a lag here. A graph will soon show up where, measured on false alarm, DL is not the winner. It achieves its higher recall by having more false alarms. And when we talk about some balanced measure, area under the curve of false alarm versus recall, we get this graph here. And here you see, firstly, DL's not winning most of the time. Certainly on the far right-hand side, you can see red numbers high above the blue. So there are certainly cases where DL does better than non-DL. But on the left-hand side, there are certainly cases where non-DL does better than DL. Now, my students don't accept this at all. They say, no, we have to do something about this. And so they've lent in and said, how can we fix deep learning? And they're now talking about loss functions, and they're talking about methods for doing fuzzy sampling to improve the green results. But here's the kicker. The techniques they're finding look like they apply outside of DL. So we're finding ways to improve DL, but if we take those ways and apply them to, say, support vector machines or a random forest, those other algorithms are getting better as well. So DL is certainly a source of inspiration and innovation, but at least in our lab, it's like DL is a stepping stone. We use the DL as an experimental platform to learn stuff which we can then apply to lots of other algorithms and improve things elsewhere. So you've heard a lot from me, so we're going to wind up soon. I think there are many other people you should be listening to. There are definitely more people to listen to. So Dave Scully's paper on technical debt in machine learning and Google's well worth a read. I sat down with Tom Zimmerman and we talked a lot, and he's told me many clever things. We wrote that up for an IEEE software article about the future of software analytics. I like my paper on SE for AI, but that could just be a proud father. Recently, IEEE software had a special issue on AI and SE, and there's some really good articles in there. Highly recommend that. I really think we should all read Yuri Brin and others' papers in Science about preventing undesirable behaviors of intelligent machines. That's a really important paper to read. I find Kathleen Walsh's writing insightful. Like, I actually disagree with her. Like, here's her very famous recent column about why Agile misses the mark for AI and machine learning. And I think it's really important to read what she said. And I disagree with what she says, but it's so insightful what she said. It's like a breath of fresh air. So it's really great to read her stuff. Okay, so I've talked a lot about the future of SE, and surprise, surprise, I think there's a very strong AI component in there. I've talked about something called Software 4.0, and I've forgot to add it here. Also, an engineering framework that's been incredibly successful for literally dozens of my PhD students and literally hundreds of papers. And that framework is GATE. And I want to suggest to you that when you learn about AI and think about AI, don't start with decision trees as a separate algorithm to clustering. Instead, think GATE and think how you can refactor and combine all these things. I want to say AI for SE is different. One thing in particular is there are these astonishing simplifications in SE for AI. I think that simplification is incredibly important for ethical reasons in society today. I think that if we don't just accept AI tools from other communities and be critical about them, we can improve those tools in interesting ways. And that was the deeper learning stuff. And so my take-home message is that AI software is software that you can understand. If you're someone who's saying, I don't understand AI software, and you're leaning back, please lean in. AI software is software. And the people that understand software are you. So please get to the point where you can start refactoring different AI tools. So that's my test for you. You can understand AI tools when you can refactor them, combine insights from multiple tools into one thing. And that's my Software 4.0 and my GATE thing. And recall that Software 4.0 was AI understanding people and people understanding AI. I think we should be more critical. We shouldn't just write a paper by taking some AI tool from somewhere else and applying it to our data, because SE for AI is different and these tools need tuning. And I think it's really important to match the complexity of the analysis to the complexity of the data. And I think some of the deep learning research in software engineering is a great counterexample where too complex a method has been applied to too simple a data. And I think in this talk, you've seen ways that we now can characterize the complexity of data mathematically, and we can find regions where very simple methods can be engineered. And I recommend that to you. And that's my talk. Questions or comments?
Thank you, Tim. Let's give Tim a round of virtual applause.
I can virtually hear that.
Very good. We have about 5 minutes for questions, so we have multiple channels to ask questions, but the preferred one is for you to turn on your video and your microphone and just ask right out. But I also see questions coming in on the Zoom chat, which I will read out unless somebody unmutes themselves.
Where should we focus? Where should we?
Peter Rigby. Great talk. I think beautiful talk, FSC Disneyland talk, which was a good talk too. My question was, I really like your gate idea, but one thing that I've noticed a lot of the time is the data itself, like just cleaning and processing the data takes a vast amount of time. And a lot of time, what I see students doing and what I've done myself is trying to clean all of the data when really just a simple set of predictors within or parts of that data is more useful. So would you add that to your gate or
No, it's there already. I mean, so you're talking about the data processing method.
Yeah, like by the time you get to the end and you're actually applying different models, you're almost done, right?
Well, quite. I mean, and there are so many jokes about that. But notice that all the way up and down the cycle, I'm taking feedback from the domain. Like the process of cleaning the data, like that's not a black box. If we lean in and look at what people do when they clean the data, they're applying certain biases, they're finding areas of interest. And I'm telling you that what I'm calling gate is something to help you in that data cleaning process. That's not a trivial detail at the front. That's actually something where my kind of AI tools can actually help you. And if you look at, I've lost it here. If you look at Mr. Tu's paper at TSE on emblem, you'll see a whole paper devoted to that cleaning process using these sort of tools.
Right, other questions who want to unmute themselves? Otherwise, I'll start reading from the Zoom chat. Okay, maybe we'll take one from Zoom then. The question here is, where we should focus more: improvement for AI approaches, so machine learning algorithms, or finding more relevant data set for training the existing machine learning algorithms for AI-based software engineering?
Why not both? If you come back to this slide, there's this point where we do feedback and we say, you know, hey, listen, we've looked at the data, we've found regions where it's very similar and homogeneous, and we've found holes. So if you look at what the active learning cycle does, active learning is a data collection cycle. It's saying we can, if you're doing effort estimation, you can very quickly get descriptors of software projects, but to lean in and ask, how much did it actually cost you to build that thing? Companies are very reticent to offer that. And so you want to minimize that. So my answer to you is, why not both? And my answer to you is very much the same as to Pete. I think there are AI tools to help you in both.
All right. The next question is about comparing deep learning and non-deep learning. When we look at the green line and statistical significance, does it analyze effect size? Is the effect size significant enough to justify the engineering costs for deep learning?
I'm trying to find my standard statistical package. If you ping me, old SK, I've got, I'm sorry about this. I can only find you my old Scott Knott code, but here is my standard Python code for doing the Scott Knott test. And if you go through it, you'll see there's a non-parametric effect size test, Cliffs Delta, and you'll see there's a non-parametric significance test, bootstrapping, and you'll see the Scott Knott procedure of recursively descending. So when I give you stats, I give you significance and effect size. Okay. So yeah, my green lines pass these rules. Okay. Now your second part is it's giving up to justify the engineering cost. Well, yeah, sometimes, yeah. Like supposing let's move away from software engineering. Supposing you're doing wavelets, you've got 10,000 wavelets, and you want to put that together. I'm so attracted by using the bottom couple of layers of a deep learning network to do automatic feature engineering to combine the signal from 10,000 wavelets. I think that would really be it's a really powerful framework, and people have done that. My point is, I'm not seeing that in the things we've called software engineering up until about 2 years ago. Since then, we've seen lots of automated cars and vision stuff, and that's becoming part of software engineering. And it maybe we need to understand the complexities of those kinds of data sets and know when to apply. So I think the short answer to your question is, implement a complexity measure, sort your data by that complexity measure, and apply deep learning for the highly complex, high-dimensional data.
Great, thanks, Tim. Any other questions? Maybe we have time for one more at most. All right, let's thank Tim. Fantastic keynote. Virtual applause again, maybe. There's also the little Zoom reactions that we can use to show clapping hands next to our faces.
Wow, the amount of love that gives me is measured in micro, but the volume is so large that I'm feeling a wave of love here. That's fantastic. Thank you so much.
Fantastic. Thank you so much, Tim. So in this Zoom session, we'll continue with a technical session on quality improvement. And in the parallel session, we have a technical session on human and social factors. So I'll hand it over to the next session chair. I see Valentina is already there. Fantastic. Thank you, Tim.